Welcome to Module 6. Today we'll be talking about data preprocessing using MindMeld's text preparation pipeline. So what is the text preparation pipeline? It's MindMeld's text processing module which handles the preprocessing, tokenization, normalization, and stemming of raw queries. It has extensible components that can be configured based on language-specific requirements. It offers components that integrate functionality from spaCy, NLTK, and regex, and many other popular NLP libraries. The text preparation pipeline processes text in the following order: the preprocessor, tokenizer, normalizer, and finally stemmer. At the very end, you have the final queries that are used by the machine learning models. Let's take a closer look at an example of a text preparation pipeline. The diagram below is a visual example that uses spaCy for tokenization, as you can see here. It has a number of normalizers that are applied in sequence to the text. For example, remove beginning space, remove any trailing white space, replace underscores with space, lowercase, and ASCII fold. Why do we normalize text? Well, the reason you'd want to normalize text is that you're able to bring the space of the input to your models down to something that your models can understand better. So instead of having it have to understand and learn the nuance differences between capitalization, if you fed your models all lowercase data, it would be able to converge on your data much faster. Moreover, for the tokenizer, there are different ways of splitting up text depending on the language. In English, it's a white space based language. However, this may not be the case for something like Japanese or Chinese. And that's why we use the spaCy tokenizer, because it's a third-party tokenizer that is able to understand these language-specific nuances and split the text accordingly. So now we see that we have different ways that you can process the text based on your language-specific requirements. How would you go ahead and specify these rules, or what should be used by your MindMeld application? Well, you just go into your app's config.py file and add in this dictionary. So it's easy as that. If you don't define one dictionary like this, a default would be used. Here is the default dictionary. It has 0 preprocessors. It uses the whitespace tokenizer. It uses the 12 system default normalizers that just remove spaces that are trailing before and after the text. It might add an extra space between an apostrophe s to treat an apostrophe s as its own word. It may also run the lowercase or ASCII fold. ASCII fold finds ASCII equivalents to various ASCII characters. Again, this brings down the space of the input to ensure that your models converge better. You can also specify some regex normalization rules. There are more details in the documentation to do that. But in essence here, you can specify a regex pattern that would capture some type of text, maybe emails, and then you can specify an action that could be to separate out the @gmail.com, or maybe you might remove that entirely. You can specify the stemmer. You can also specify specific special characters that are key to your application that you don't want the text preparation pipeline to touch. If you specify these characters, it would not modify any token that included any of these characters. So again, here are our defaults. The preprocessors, none. Normalizers, the 12 default MindMeld regex rules, lowercase ASCII fold. The whitespace tokenizer, and then the stemmer is automatically selected based on the language that you have available. If it's English, it'll obviously use the English NLTK stemmer, and if it's supported in any one of these languages, it will use the snowball stemmer. And lastly, If the language is not English and is not supported by NLTK's snowball stemmer, well, you just won't have a stemmer, and you will use the no op or no operation stemmer. And lastly, these are the special characters that MindMeld does not touch by default. So now let's talk about each of these components and take a closer look at their base classes and how you would go ahead and implement a custom version of these components in the text preparation processor. So the first one is a preprocessor. We use the preprocessor when you have instances where the text needs to be cleaned up right from the get-go. And this is pretty common with ASR, or automatic speech recognition. What happens with ASR is that sometimes phrases that sound one way might sound similar as another set of words. For example, if someone in a meeting room said, "Hey, let's call Prashant ready," the system might accidentally mistake Prashant ready as croissant ready, and this would clearly be a mistake. Now, ideally, we'd want to fix the ASR system itself so that it never makes this mistake from the beginning. However, that's not always feasible to do in every instance. And so, kind of the workaround here is to identify that, okay, well, Prashant ready is commonly being mistranscribed as croissant ready. Why don't we add a specific rule to go in and do the opposite and switch it back? Because it's pretty unlikely in our particular application that someone is going to utter the phrase croissant ready. So here we have our preprocessor base class, and it implements one abstract method called process, where it takes in text. Right now it does nothing, just pass. What it should do is take in this text and return some other string. That's perfect. So now let's implement or extend this base class. So we'll make our ASR preprocessor right here, and we will again implement the process function, and our implementation would be to use the string.replace method and replace any instances of croissant ready with Prashant ready. This should resolve our ASR transcription issue. Similarly, we can create custom tokenizer. So what is a tokenizer? It's just a way for us to split up the incoming natural language query into chunks, and this is what the model will use as input. Now, the way you split up the chunks can change how the model trains or interacts with our data. In English, we typically use the whitespace tokenizer, which essentially does a dot split on the incoming text. But first, let's take a look at the base class for tokenizer. Again, it's a class called tokenizer, and it implements .tokenize, where it takes in a text string and returns a list of dictionaries. Now, the reason we return dictionaries and not just the individual strings is because we want to also keep track of the starting position for where that particular token existed in the original string. And this helps MindMeld do a number of mapping operations in the background, but it is key that these calculations are done correctly. So let's make ourselves a character tokenization, which is a tokenizer that splits text at the character level. So here in our function, we say, okay, we're going to extend the tokenizer class in our character tokenizer, and then we're going to iterate through every character in the text. And as long as it's not a space character, we're going to append the index for that character as well as the character itself. So let's take a look at an example. This tokenizes the phrase "Hi Andy" in the following manner: HIANDY, and you notice that we have the numbers 0 and 1 for HI, but 2 is a space character that is skipped, so we didn't store that. And finally we have 3, 4, 5, and 6 for Andy. And this shows you how you can make a custom tokenizer. Of course, you can add as complex of logic you want inside of this tokenizer function. In our case, we're exploring the example of the character tokenizer. Now let's talk about a custom normalizer. Well, a normalizer is a way to essentially normalize your text or remove any odd behaviors that you might see, weird characters, additional spacing, or just swapping characters for another. So you can delete characters, you can add characters, and you can replace characters in the normalization step. So again, the base class is quite straightforward. It's the normalizer class with one abstract method called normalize, takes in some string called text, returns a new string called normalized text. So here let's make a very, very, very simple normalizer called the lowercase normalizer. Well, it extends from normalizer, and it extends from normalizer, and then it implements the normalize function, taking in a text and returning text.lower. And that's it. Next, let's talk about a stemmer. What is stemming? Well, say you had the word fishing. You can reduce that to fish. Again, this brings down the space of words for our model and allows it to converge and understand relationships between words a lot faster. So a base class stemmer would take in some string of a word and return another string, which is the stemmed version of the word. It would take in fishing, return fish. Let's implement a spacey lemmatizer. We're essentially doing the stemming, but we're going to use the spacey module in order to do it. Spacey is one of the top class natural language processing libraries that allow you to process text. In order to use it, we first define our NLP object, which does spacey.load and loads in the en core web sm module. What this does is that it is preloaded with an understanding of kind of the language and the rules to follow. This is a third-party library that we are integrating in using MindMeld. So now that we've done spacey.load and we've loaded in this module, we can access spacey using self.nlp. So now in stem word, we take in our word and we pass it into self.nlp, and this creates a doc object. We can access a lot of information from the doc object. In this case, we're interested in accessing the token.lemma underscore for each token in doc. And all that means, the lemma is just a short form or the lemmatization of a given word. So the lemma for fishing is just fish. So we grab all of the lemmas inside of our particular word and we just join them together with a space character and return it. And this is a spacey lemmatizer. Now let's go ahead and put this all together into our application. If you had your own application and you wanted to make a number of these custom modules, how would you go about doing that? So first, you would create a Python file in your root directory called textpreparationpipeline.py. In here, you can import all of the base classes for your application. So we've imported the preprocessor, stemmer, normalizer from mindmeld.textpreparation. Now we just make our custom implementation. So here is our ASR preprocessor that makes that fix between croissant ready and prashant ready. Here's a gerund suffix stemmer. This just finds anything that ends with eng and gets rid of those last three characters, and then returns that word. And finally, we have remove explanation as an example normalizer, and this just does dot lower. Actually, it should just do a dot replace on an exclamation mark. But finally, we can then implement the get text preparation pipeline function. Now here we'll first create a default text preparation pipeline and then override it with these custom objects that we've just created. So we could say text preparation pipeline is equal to, and we import this text preparation pipeline factory from MindMeld, and we use this function dot create from app config, which is the current config in the current directory. That's what this dot / indicates. And then from there we can override each individual component. So we can say dot set preprocessors, and you give it a list of preprocessors, in our case just the ASR preprocessor, and we instantiate it. So now it'll update its preprocessors to point to this list that we specified. Then update the normalizers. So in our case, we want to append the remove exclamation. We don't want to reset all of those 12 defaults we discussed earlier. And then next we can set the stemmer to being the gerund suffix stemmer. And finally, we now return this updated preparation pipeline. There's one last step here. Now we've defined this function for get text preparation pipeline. We want to pass this in at the root level of our application so that we ensure that this preparation pipeline is being used. And that's the second step. Now let's take a look at our root init.py file without a custom pipeline. Simply is from MindMeld import application. The application is created, and then we have our handling logic, which is here a welcome function. Now we're going to change 2 lines in order to use our text preparation pipeline. We're going to add this import of the file we just made, text preparation pipeline. We're going to import that getter that we just defined, the get text preparation pipeline getter. And now in the root application, when the application object is being made, we add in this new parameter called text preparation pipeline, and we pass in this function, get text preparation pipeline, and when this function is called, it will return our custom text preparation pipeline and put it in at the root level. This ensures that the application is using our text preparation pipeline. Thank you for watching. This concludes the section on learning how to define and use a custom text preparation pipeline for MindMeld applications.